Alright, so this particular class is going to be on recognizing voltage. We're going to start off with the word nominal and what the word nominal means. It just means like every one of these different scenarios, it doesn't exactly have to be at 120 or 208 or 277 or 480. There's a 5% plus or minus difference in it. So the word nominal means varies. You'll see this little circle with a cross through it. That is going to be your phase. So if it's a three-phase, single phase, you'll have that little symbol. The first set that we're going to be going through is 120, 240 single phase. Your normal coloring for that is going to be black, red, white, green. From line to neutral, you should have 120 on A, B, and C. On line to line, you should have 240, or I guess not A, B, and C, A, B, and then 240 on it between A and B. It's a three-wire system. So meaning you have a hot, a neutral, and a ground. And then obviously your green for your ground. So the next system is going to be the 240-120 three-phase. It's a delta system. This is kind of the weird one in comparison to the rest of them, because your A phase is going to be at 120 from line to neutral. Your B phase is going to be from line to neutral is going to be 208, which is weird. And then C to neutral is going to be 120 again. And then when you do phase to phase, you're going to have 240 on all the phases. And that's why it goes 240, 120. Because it's on a delta system versus a Y system. And per the NEC, code reference 110.15, the high leg, or the B phase, or the crazy leg, whatever you want to call it, has to be orange. Just like the ground has to be green, and white either has to be white or gray depending on the voltage, but the NEC does require that it is orange for the high leg when it's in this system. So it would be an essential, like if the B phase was the crazy leg, which typically they are, it's going to be red, orange, blue, black, orange, blue, white, and green like normal. So everything would be the same minus the crazy leg. So this has to be identified so that you do not put a 120 circuit on the B phase, because then you have the potential of fucking up a receptacle, anything like that. Or just like, putting a computer on a 208 system would definitely screw that up. Another fun fact about this particular field is you cannot run boats in it. What I mean by boat is you can't put three phases on one neutral, and that's because the NEC says very specifically that you cannot do that if it's different voltages. So if it's 120, they all have to be 120. And because you can't have 208 going down the neutral, potentially screwing that up.
So they can't share neutrals, pretty much.
Yeah. Correct. So, I mean, and you're supposed to run individual neutrals nowadays anyway, but, just for the sake of saying it, you cannot have, you can't share neutrals in this specific system ever, even before the new code has come out. So that's the crazy leg. So our next system is more common. It's going to be the 208 120. This is going to be in your normal commercial panel. It's 3 phases, so 3 ungrounded circuits, 1 neutral, so 4-wire circuit. Line to neutral is going to be 120. Line to line is going to be 208. Black, red, blue, white, green is going to be your color combination for us. Fun fact about the NEC is these colors can be completely different. White and green have to stay the same. So this is just a industry standard, but this is also our standard, is that we're going to be doing black, red, blue, white, green on this particular system, the 208 120. Then we move down to 480, which is just going to be your normal lighting panel, motors, HVAC systems, stuff like that. Line to neutral, 277. Line to line, 480. The normal color coding that we use for this, and once again, doesn't specifically say that these have to be the same, but gray and green do have to be the same. So brown, orange, yellow for A phase, B phase, C phase is going to be our color combination for the way we run things, and that is the 480 277. So there's like a little fun fact I'm doing here at the bottom. And this is more tailored towards you, buddy. Why does the continuity ring out when you're testing secondaries on a transformer?
Not too sure. Put it near the transformer, to be honest.
All right. So the reason why it rings out if it's hooked up is because the way the transformer is hooked up. So the way a transformer is installed is you have this little like box essentially with 2 holes in it. So the way that a transformer goes is the windings go around it. So you got your primaries will be the ones on the bottom, and your secondaries will be on top. And then same thing. So this is a big metal plate that is going onto the transformer, and they're all on the same plate. So when you put your leads to it to see, ground and like let's just say A phase, and they come to here, this thing's been grounded out already. So that's already been attached, and then this goes attached. So that's why you get the continuity ring whenever that goes down. So like if you put like your continuity tester, like red and black, you put the black on the ground, and then you're trying to see if this thing is ringing out. And you do this primarily when you're testing your new wire setup to see if there's an issue pulling the wire in, essentially. And you're like, oh shit, I want to make sure that this thing's clear of any faults. So if you already have it hooked up, it's gonna read continuity and scare the shit out of you, because you're like, oh fuck, it's ringing out. But then you'll go to B phase and C phase and see that those are ringing out too, and it's because they're all connected. Everything's connected inside the transformer, bringing that voltage down.
Okay.
So
it's ringing out because your voltage coming into the transformer that you want to dumb down through the transformer is connected to your other side, which is kind of like a line load situation. Your line coming into the transformer and your load coming out of the transformer, because those are all connected. That's why it's ringing out?
yeah, because it's so I'm sure you've seen this symbol where it goes like that. and then it's like A phase, B phase, C phase on the XO side, which is your secondary side.
Yeah.
So what this symbol is basically telling you is that all of this is hooked up together. So like when you put your ground to A, or sorry, one thing on ground, one lead on ground and one on your A phase, those will ring out because the transformer itself is grounded. So everything's grounded, connected, dumbing this whole thing down to 120 or whatever the fuck it is. So that's why you get that continuity ring out. So the true way to test it is if you wanted to make sure that there wasn't any faults in the system, is unhook it from the transformer and then do ground to your line on open line, not hooked up to anything, not to any fuses, not to, just like point A, point B, see if there's any faults.
Okay.
And that's what we did at that one Varus project to figure that issue out and why they were messed up. So that is today's little fun fact lesson. Fuckers.